Hello all. In this video, we're going to take a look at an example of the lowest costs first search, our variation on Dijkstra's algorithm. And hopefully this will help you to see both how the algorithm works, but also this idea of our search tree. We'll use that to illustrate the order in which we're examining nodes as well, at least for part of the search space. So this is an interesting example because it has kind of a topological shape to it. There's a region that's a grid, and we're searching in that space, which is in some ways intuitive for us, but it can also lead you to forget that these algorithms apply to all kinds of problems. And the state space does not have to be spatial in nature. It just has to be a collection of discrete states with connections between them. So that includes a wide range of examples. But let's take a look at this one. All right, so here's our example. It's a terrain navigation problem. So what is the problem? We have a grid space, and so here are the indices of the coordinates that we're going to use for positions in this space. We're going to use rows and then columns to describe the different elements, different cells in our grid. And you can see that the white cells here, those are the grid cells themselves. Each cell has a number in it, which is essentially how difficult it is to cross that particular cell. So maybe you're imagining this is a robot and it's traveling around, and there are certain areas that are very cluttered or where it has to climb steeply. So those have higher costs, and then there are other cells that have a low cost where it just needs to pass through. They're fairly simple and straightforward. That's the realm that we're looking at. What we want to do is to figure out what path the robot should take, the agent should take, to get from our starting point, which is our green cell, to our goal, which is our red cell. And you can see that if it just went straight across, it's going to pass through some of these really expensive places. Cells in the grid. So maybe it would be better for it to go around the outside, and we want to figure out if that's the case. So we're going to use lowest cost first to handle this situation. So each state can be captured. Because this is a static world, the weights aren't going to change over time. Each state can be specified just by its coordinates. So the starting state, for instance, is 3, 0. That's the coordinates, and that tells us everything we need to know about the states in the world. Because this is weighted, we can't use breadth first search or depth first search. We have to use something more elaborate. This is just a reminder of lowest cost search. It keeps the frontier in a priority queue organized by the path cost, the cost that has accumulated so far or accrued so far. It's always going to choose from that frontier queue the state that has the minimum path so far and a path cost, and it will not revisit explored states. If we find a new path that goes to an existing state, we will keep whichever has the lower cost. Those are sort of just a summary of the main points of our search. In this demonstration, I am going to color code the states, the grids on the map, the grid cells. So any grid cell that is currently a frontier will be marked in yellow. Cells that have been explored and we're not going to consider anymore will be in blue, and the current state that we are currently considering will be shown in purple. I will also show you what the cost accrued so far is, and I'll show you the priority queue, and at least for the first few steps I'm going to alternate by showing you also a search tree view of what this algorithm is doing. All right, so here we're starting off. Our starting state is 3, 0. This is a situation, this terrain example was what I had in mind. This is a situation where the initial cost is not 0. We're in this cell, we just assume that we're going to accrue that cost of 1. That's because this problem is slightly different from in how it's formulated from some of the others. Often we think of the action as being the thing that causes the cost, but here the cost is intrinsic to the states themselves. So it's as if we have weighted states rather than weighted edges in the graph. It's not a huge problem, but this is the way that we handle it, is we just set the cost to be non-zero initially. So because we're at 3, 0, our initial cost is 1. We set up the priority queue at the very start with our start state in it. That's 3, 0 with a cost of 1. And then the algorithm says pull that out of the queue, mark it as explored. So after this step, it will be marked as blue, generate its neighbors, and if they have not been explored and they're not already in the queue, add them to the queue with the new cost. So notice that the cost for this 4, 0 is 1 plus 1, so it's 2. The cost for 3, 1 is 1 plus 2, so it's 3. And the same for the cost for 2, 0. All right, if we wanted to, we can take a look at this as a search tree. And it looks like this. We have 3, 0 as the root of our tree. Its cost is 1. It's been chosen as the first state to come out of the priority queue. And so we have its 3 children and their costs. All right, the next step is that we're going to take the front of the priority queue, the 4, 0 with a cost of 2, and we're going to expand it. We are going to explore it. So we will mark it as explored after this step. We will generate its neighbors and we'll see what happens. So in the process, we're going to generate 2, 0. We're looking at 4, 0. We're going to generate 3, 0, 4, 1, and 5, 0. 3, 0 is already explored, so we don't reconsider it at all. But the other 2 are brand new, and so they get added into our queue with new costs. So we take the cost of 4, which was 2, and we add 1 to it or add 2 to it, depending on the state. All right, so we've now explored outward a little bit. If we look at that in priority in search tree terms, you can see 3, 0 is now marked as explored. 4, 0 is our current one being expanded, and it has these 2 children with their costs. When we go around our loop again and we go to select the next node, it would choose from among the ones that are marked in yellow here, and it'll choose one. We don't really know which one, but if there's more than one that has the lowest cost, it's going to look for the lowest cost. There are 3 nodes here that all have a cost of 3. In practice, any of them could be chosen. I'm going to take them kind of left to right just for simplicity, but in actual fact, it would depend on your implementation of the priority queue, which one ends up in the front. So in this case, we're going to have 2, 0. That was the one I put at the front. So we're here at 2, 0. It's marked in purple. We're looking at its neighbors. It has 3 neighbors. The first two are brand new. We've never seen them before, so they're going to add to the queue, 1, 0 and 2, 1. But when we look at 3, 0, again, it's been visited, so it's been explored, so it doesn't get added to the queue. And that looks like this. Now our fringe set has elements that have cost of 3, elements of cost of 4, and an element of cost 6. We're going to choose from between these 2 that have a cost of 3. I'm choosing 3, 1 next. 3, 1 is our first case where we actually have neighbors that are in the frontier. So if you look at 3, 1, its neighbors are 2, 1, which is already in the frontier, and it has 3, 2, which is brand new, and then it has 4, 1, which is also already in the frontier. Both of those are in the frontier, but if you look at the cost that would accrue, 3, 1 has a cost of 3. So if we then go to 4, 1, that's going to have a cost of 4. That's higher than the current value that 4, 1 has in our queue. And the same for 2, 1, the cost was 6. This is going to have a cost of 6 also, which is no better. So we'll just keep the original. What would change if we actually changed things up? Well, it would, one of the things that I'm drawing in here, I haven't even drawn attention to it. I am drawing these little arrows. The arrows indicate who's a neighbor of who. So what path did we use to get somewhere? So like for instance here with 2, 1, right now the path says go from 2, 1 back to 2, 0, back to 3, 0, and then that's the reverse of the path. If it was better to go through 3, 1, we would change this node, this state, so that instead of the arrow pointing to the left, we'd have it point downward. This is kind of a way to view the search tree. I am drawing out the search tree also just so that you can see it in both forms. So if you have any question about the original priority queue and then the priority queue we ended up with, make sure to let me know in the comments or reach out to me otherwise. All right, so here is where we've done. We're looking at 3, 1. It has 3 neighbors. 2 of them are no better or worse than the existing nodes we already had in our fringe, in our frontier set. So they just get eliminated. They aren't kept, they aren't added again to the fringe set, they just go away. And this is the only node that will actually stay. All right, next up is 4, 1. It also had a cost of 3. So 4, 1, let's see, 3, 1 is already explored. 3, 1 is already explored. 4, 2 is brand new. 5, 1 is also brand new. And I guess one of the other neighbors would be 4, 0, but that's also been explored. So we won't visit that one either. So we get 2 new nodes added to our queue, but not much else happens. And in our tree, that looks like this. So then the question is, I'm not going to keep drawing this tree because this will take me forever if I have both the tree and the other representation. But what I would like you to try to do on your own is continue this tree as we continue to explore this example. Continue this tree and see if you can draw out the whole thing and understand exactly why the decisions are made the way they are. Right now, the next time around, we're going to look at this fringe set, which has 1, 2, 3, 4, 5, 6 elements in it, and we'll look for the lowest cost. That would be either 1, 0 or 5, 0. Those are both cost 4. So one of those would be chosen, and that's what would happen to move forward. All right, here I'm choosing 5, 0. I put that up here in the top. If you look at 5, 0, 4, 0 is already explored. 5, 1 was already generated in the queue, and coming there from 5, 0 is actually more expensive. So we had a value of 4 where we'd add 2 to it to get to 5, 1. And that's no better than the old path that we had, so we wouldn't update it. But we do get a new value 6, 0 that comes on the scene. So now we jump up to 1, 0. Nobody was in the fringe. We had 1 neighbor that had been explored, but 2 new neighbors that get added. And notice our costs are going up just overall. Now we've got 3 nodes that have cost of 5. We'll pick those off one by one. So we're looking at 5 and 1, and we expand that out. Notice we get some big costs coming in as we start to hit these expensive grid cells. And then we go to 4 and 2. We push that out as well. And again, we have some that are already in the frontier set, but the new path is more expensive than the old, so we won't take it. We jump up here, and now we're looking at 0, 0. It only has 1 unvisited neighbor, and it's not in the fringe, so we add it. We jump back down to 2 and 1, and it's more expensive to get to 1, 1 from 2, 1 than it is to get to it from 1, 0, so we don't do anything. And now we're looking at 6, 0. And actually, this is a case where we've hit a dead end in a sense. We've already looked at, there are no other neighbors of 6, 0. We've already looked at its 1 neighbor, and we're not really adding anything to the queue at this point. All right, so notice how it's jumping around, but we're very gradually expanding. I'm just going to let this expand. Most of the time you see when we get another path to one of these, to a state that's in the frontier, most of the time the new path is more expensive, but it is not guaranteed to be the case. That actually can be different in other examples. It looks kind of like we're so far we've kind of evenly been spreading out, but considering that we started here in the middle, we would expect it actually to be a little further out. So it's not really pushing to explore this midsection where the values start to get really high. It's kind of going around the edge, which is just what we would want from this algorithm. All right, and here it really starts to do that. So 0, 3 has a cost of 10. And it has this neighbor 0.4, which has a cost of 12. That's pushing pretty far on that upper level rather than the lower levels where things get more expensive. The grid cells get more expensive. But we are going to come back and explore some of those levels as our cost for our what's looking like our most promising path. As that cost goes up, we will come back and check some of those other routes to make sure there isn't a shortcut that we might miss otherwise. If there was just a little channel, a canyon in between some of these expensive parts in the lower section, we might find that that's a better way to go. All right, so we were looking at 4.3. Now we're jumping back up to what's looking like our best path. And then we jump back down to check 5.2. But you know, most of these neighbors are just, the expense keeps growing every step we take, so we end up not continuing to explore those paths. We try this one in the middle. We're going to jump back down again. We're just kind of pushing those out a little bit as our costs grow for our roundabout path. But then we come back to the roundabout path because it's still looking like the best path to get there. It has the lowest cost. Again, try some others, but we're almost there. Now notice here, when we looked at 2.6, one of the neighbors was in fact our goal state, but we're not done. The goal state is getting added to the frontier. So 3.6 is now in our queue, in our frontier queue, but it's not at the front of the queue. We're not done until it comes to the front of the queue and is selected. So we do a little more searching, and then we pull 3.6 out and we say, we have found it. Now, notice these arrows that I've been drawing, they're actually often implemented in practical implementations of this as a data structure, because from them I can start at the goal and I can reconstruct the optimal path by following the arrows. So from the goal I would go up and then over and then down, and that would take me there. And really what I have is an optimal path from anything that has been visited. Certainly the things that have been explored, what I have is the optimal path from there back to the start that I could recreate. All right, so this has given you I hope a sense of how lowest cost search works. We're going to stop there. In another video, I'm going to take a look at a program that I've written that you're going to work with in class and also on the homework that implements this kind of a grid, both an obstacle-based grid and a terrain-based weighted grid. And we can explore several of these different algorithms in that context, but I'll do that in a separate video. In the meantime, I will see you very soon.